Okay, the last week, wow. Well, there's good news. If you have checked the academic calendar, this you would think that is the last hour, because on Friday we got New Year's first day holiday, and next week, Wednesday, was out of the academic calendar. You may have seen this if you've checked, but there was something strange about the academic calendar, because the academic calendar started on a Thursday some time ago, 3 months ago, and it was ending on a Tuesday, as if Wednesdays would stop happening in 2021. They've corrected this. They didn't announce it yet, but they are going to change the academic calendar. And next week, Wednesday, we have 1 hour more. This is very good, because there were 2 live codes that I wanted to do before I finish. I'm going to do one of them today, which was about interrupts and GPIO, after I finish theoretical stuff of timers. Then next week, I'm going to do the timer live code. We're going to do lab timer. And we'll finish with maybe a sample question for the final. And it's going to be over. Before we start, any questions? No, you're tired of and sick of microprocessors EE315. I understand. Maybe you are sick of 2020. Everybody's sick of.
Aynen öyle hocam.
Yeah. Let it finish. Okay, let it finish nice with microprocessors. This was the last thing we've learned. I told you I love this diagram because I teach 1 hour of lecture. And I talk about everything. There's this control register, there's another register which does this, and there's another register. This simple diagram explains it all. It explains it all. It has everything. Which pin does what and when. It does it when it's 1 or it does it when it's 0. You don't have to check the data sheet. It's all here. And it's fantastic. In that sense, let me remind you, we had 3 control registers to control the timer in this device. 3 control registers. The first of which was the control register, status control register. As all registers of the system, it is 32 bits. However, most of the bits being reserved. In other words, not used or don't care. All the same nomenclature. And we were using only 4 bits. Bit 0, bit 1, bit 2, and bit 16. Okay? So if you just consider this 32-bit as 2 parts, the low part and high part, it is the least, the bit 16 is the lowest bit of the high part. Because in architecture, we do these low part and high part things. If you go into an advanced architecture course, I strongly recommend. Find it on some university, but after 2020, you don't have to find it in a university. Go find an advanced architecture course on the internet and take it if you're interested. And you'll get to know these definitions, a high half, the low half of a 32-bit register, or quadrants sometimes, whatever. And they all had some purposes. For example, what was the purpose of the first register? It says enable. What, for example, let's consider that I don't know the name of the word enable. I don't understand English. I'm just an Indian guy who's checking this diagram, trying to understand what it is. It is connected to an AND gate. Good. The AND gate is connected to some sort of clock with a multiplexer. I mean, depending on this pink line, one of the clocks will reach. The clock is ended with this pin. If this pin is 1, the clock will follow in. If this bit is 0, no clock will follow. So it is like an enable, like an on-off button for this device, right? Yes, that's why it's an enable. It's all here. This is how you read this diagram, guys. The second one, let's get to the first bit 2, the third one, because it's easier. Again, the pink line connected to a multiplexer. What was a multiplexer? Depending on the control signal, which was connected laterally, not from behind, laterally. Depending on that signal being 0 or 1, one of the inputs are chosen. So this input is chosen. So if this pink circuit is 0, the external clock is chosen. If this pin is 1, multiplexer allows this signal to be fed and just stops this signal. That's what multiplexers do. In that case, we've got a clock inside it, which is running the device, which is running by default in 16 megahertz. So if we choose this one, it's going to be 1. Good. And the other one was, so they were connected to a counter. What was a counter? In digital design, you have seen what a counter circuitry is. A counter is, you feed a clock to it at each clock edge or level, depending on the type of the counter. It increments or decrements. It could be a forward counter or a backwards counter. It doesn't matter. Okay? You've done the design of a digital counter in digital design using registers and flip-flops. You know how it is. If you know how the design of a flip-flop, well, you can design a flip-flop using digital and analog electronics, right? You know how to do it. You know how to do digital electronic devices from circuits and systems. You know how to design circuits. Guys, that's how you understood how computers work. You are the only engineering field who totally understands how computers work. Circuits, then electronic circuits, digital circuits, flip-flops, logic designs, from logic design to computer architecture, from computer architecture to microprocessors, from microprocessors to embedded programming, the next semester's elective course. So it is connected to a counter, which is decrementing. So if it's enabled, it counts. Good. When it hits 0, because it counts below, downwards, it decrements. Is it 0? Yes. Then read this value in this register, which is also 24 bits. Just load it. So when it is 0, most probably there is a reset bit here, which is connected to this. It resets itself. Do you remember the registers and their reset bits or copy bits? Depending on that being 0, all the values were transferred. Using your basic digital design tools, which you learned in digital design course, you can construct this circuit from simple registers and flip-flops, actually. Good. And when it's 0, this read-only bit is also set to high. Good. 3 registers explaining all of the functions. And finally, when this count flag was 0, when it hits 0, it creates this flag. This becomes 1. And if this bit is 1 as well, 2 1s, this end will create the SysTick interrupt. So if you want this device to create an interrupt, you need to arm this device by making this 1. Otherwise, no interrupts will be able to come. Do you remember what was the analogy we used for arming that device? The shop being open or the shop door being locked. So if you make this 0, this AND gate will never give out any value other than 0. The shop is locked. This is how you arm it. This is the arm bit. Why am I telling you this? Because we were talking about the busy wait operation, initialization for this device. Next I'm going to talk about the interrupt initialization of this device. And you're going to see how we initialize this device for interrupts. That's how we are going to be building the lab timer next week. Good, 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 good. Now, guys, we were talking about this operation, an initialization for the busy wait operation and a subroutine for busy wait operation using the timer. We were creating a delay. So I'll wait for 1 second. We were going on this. I'm not going to go into the very details of this stuff because if I do, I won't have time for other things. And we have very limited time now. If you remember, what briefly we did was, let me get my pen. I love my pen. Okay, so I'm going to draw it with my beautiful handwriting. I'm going to draw over the code. Guys, this part was to make this bit 0 so that it is connected to the AND gate, which was also connected to the clock. The counter will be frozen. So while I'm initializing it, I want that device to stop. That's what I do. I disable it. by ending the clock with a 0, that 0 being this enable bit. How do I do this? I make this control register totally zeros. I mean, these are reserved. You cannot write anything into them. This is a read-only bit. You cannot write anything into it. You cannot change it. It changes itself. It's read-only. And whatever I write to these doesn't matter if this is 0 because this clock is frozen. It is dead. That's why I load a 0 to R0 and write R0 to where R1 points. R1 is a pointer, which is pointing to this register. Good. Very good. It's frozen. Now I load the maximum value. Remember, guys, the reload register and the counter was 24 bits, not 32 bits, which means they have 24 bits in their register cells, which means I cannot create a number which is larger than 2 to the 24 minus 1, which is in base 10 equal to hexadecimal 00 F, 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 which is here. Actually, I was loading the maximum value. You remember these are nibbles. Nibbles are 4 bits. The very first thing we learned. And there are 6 nibbles. 6 times 4 is 24 bits. Simple operation. Good. I've set it to the maximum value. Then I've calculated how long will it take if I set it to the maximum value. I'm going to do it, don't worry. And finally, we've set the values to 101, disabling this interrupts, enabling the device, and selecting the clock source as the internal clock, which is by default 16 megahertz. Very, very good. And the next slide, we have done an operation on busy wait operation on this register, which was, this was wrong. I didn't correct it, but I'll correct it each time. So this is 16 megahertz by default, which will make 20.5 nanoseconds at each. We call them tick because it's the clock signal, but when the clock signals that reach the timer are called ticks. Why don't we call that clock signal again clock signal? Because clock signal is called the internal clock signal of the device. So if the clock signal is selected as the internal clock signal, the tick and the clock signal are the same thing. However, they are not necessarily so. If I choose this one 0 and connect an external signal, the tick of this device, the timer, will be different than the clock of the device. So that's why, to make it simpler at the context of the timer, I call it a tick. The tick of the timer. So the single tick will be 6 to 2.5 nanoseconds. Guys, this is a very nice subroutine. It waits for a certain number of seconds, which is written in R0. In R0, what you have is the number that you wait. Imagine in R0, I write 8 million, which is 8 million. I write it this way. Okay, 8 million. So if I cannot write 8 million, or if I have to write 8 million, what I just do is I go to the calculator. I just open the, let me just get it here. Programmer. In decimals, I write 8 million. 8 million is, as you can see, hexadecimal, this guys. So if, before I call this subroutine, I make R0 this value, it's going to be 8 million. And what this subroutine does is, it waits for 8 million ticks exact. How much does it take for 8 million ticks? Well, it's quite simple, because a single tick, I know, takes, not this value, 62.5 nanoseconds times 8 million. And the value is, if you calculate, since this is 1 over 16 million, it's very easy to calculate, but I'm going to be doing it in the calculator as well. 62, let me just find the, sorry. So 8 million times 62.5. 500 million nanoseconds, or over 1,000, 500,000 milliseconds, or over 5,000. Sorry, microseconds. This was the previous one. This is 500 microseconds or 1,000, 0.15 seconds, half second. So this will wait for a half second. Very nice. You can create many nice things. You know how to just make the LEDs on and off in different colors, right? Just use this timer to make different colorings. You can. It will just busy wait while it's waiting, but who cares? You can do it. And finally, before I finish the theoretical stuff on timers, I'm going to show you how to initialize the timer for, let me just clear the drawings, clear all drawings, for interrupt operation. We're going to use this next week. So how to set the interrupts? We just simply just make this bits 1. So this is the ARM bit. Remember, I told you for some interrupt sources, there are 2 arming bits we set. And for GPIO port F, we had 2. We had to just change 2 bits. Good. For SysTick timer, there is only 1, which is this. This is the ARM bit. Okay. And for this device, since it's an interrupt source, there should be an interrupt priority as well, right? Which should be by value lower than the priority defined in base pri. You remember the priorities. It is written into this address. Why this address? Because when I was preparing these slides, I've checked the data sheets. Okay. So do you want to work with the timer for an interrupt routine? What are you going to do? You are going to arm this bit. You are going to set the priority. You are going to make the global interrupt enable open. You are going to set the global priority level. And when the interrupt comes, you are going to acknowledge it. How will the interrupt come? Well, simple, guys. You've done this and you are going to do it again. Nereye koymuştum ya? Açtık, kapattık. Sen yok, açmışım. So guys, let me just open it. Okay. Bir saniyenizi rica edeceğim. Kod açacağım da. Geliyor. Remember, when we were talking about the priorities, so you can see my screen now with the code. We said that every interrupt is listed in the so-called interrupt vector table with a specific order, which is designated in the data sheet. So if this timer also can create interrupt, it is an interrupt source, then it should be somewhere in the interrupt vector table. The interrupt vector table is already written in Startup S. So the guy who prepared this Startup S, I mean, Erhan prepared this by finding it on the internet. So Erhan put this for you on the labs, but the guy who prepared it in Texas Instruments, whatever, he read the data sheet. He prepared the vector table by looking at the data sheet. It was not an easy job, but he had to understand the entire device. So if you go down at some point, which is written here, SysTick timer, there are timer 3As and timer 3Bs. I'm not talking about them because actually there are other timers on this device that I do not talk about. There are other timers as well. There is this SysTick timer, which is a simple one. I'm using that one. Actually, in this device, there are other timers. I'm not introducing them to you. You are not responsible for them in this course. Well, they are not different than this one. They have got control registers and you control them in a different manner, but don't worry. Learning one SysTick timer is enough, and we are using this SysTick timer. So I'm looking at the SysTick timer. Can anybody see the SysTick timer interrupt? guys. I can't. So God has provided us Ctrl F. That's what I'm going to do. SysTick. Yes, it is here. As you can see, it is here. The SysTick timer. One of the fundamental ones. So I name it SysTick handler, which means in my code, if I create a function called the SysTick handler, it is going to handle interrupts using the timer. Okay? Actually, this code does it. I'm going to use this code. I'm going to talk about this code today. You can download this code. Where is this code? These are all the slides, I guess. Yes, initialization for the interrupt. I'm going to go over this. We have this on the code. Let me talk about this and let me tell you where the code is. Sorry. So this is how the interrupts are set. How to set the interrupts? Guys, we set the interrupts. First, what I do is I clear the enable. I disable the device. I freeze the timer. Then I set the maximum value to a value. It doesn't matter. Most probably you're going to change it, but you can set it here. Then by writing the SysTick current register, which is read-only, by writing into it, you order it to be 0. Okay. So I write R0 and try to write 0 on it. But if this was 100, nothing would have changed. I was clearing the current timer. Be careful, guys. This is a trick question I most probably ask in the final. Finally, I set the control timer. This time I set it to 7, 00007. Why 7? Because I want to enable it. I want the internal clock, and I want the interrupts, which is 0000111, which is in hexadecimals 00007. If you initialize it like this, it is initialized and armed for interrupts. Is there a question? Good. Now guys, please.
Ben şeyi anlamadım. 5. setup'ı sanırım. LDR R0 eşittir garip bir sayı. Onu tam olarak neden o sayıyı yaptık?
Yes. Actually, why? No reason. I mean, that's where we set the reload timer, right? So the maximum value. Can you hear me?
Evet hocam.
Okay. Ya şimdi burada kartı takmaya çalışıyorum da kartı takarken sapıttı alet. Acaba dedim yayın mı gitti? Well, it doesn't matter. I'm making it something. 16 million won. If I make it 16 million won, the cycle will be n plus 1, which will be 16 million. So the timer will tick every 1 second. That's why. To make it, so the time that it becomes 0 will be 1 second, because just this value is 16 million 1 minus 1, 16 million minus 1. Okay, we are okay with that. 16 million minus 1 is in hexadecimals too. So remember this slide.
Hocam bir şey sorabilir miyim peki?
Let me finish the answer to this question. If you set the n, then the period is n plus 1, which means the time for this device to decrement will take 16 million minus 1 plus 1, which is 16 million. Are you still following? And this is the period of each tick. This is this value. So for each tick, it takes 62.5 nanoseconds. I have 16 million ticks because of the n plus 1, which makes 1 second. With that strange value, when the clock signal is 60 megahertz, I initialize the maximum value such that the time it takes to wrap from the maximum value to 0 is 1 second exact. Exact, just like a clock. Okay? To make it exactly 1 second. Because this is a computer, you can do anything exact. Okay, any other question? It was Yiğit, I guess.
Hocam şey diyeceğim. Şimdi 8 MHz ayarlamak istersek 8 milyona göre gece de 8 milyon eksi 1.
If you make it 8 million, the period it takes will be half a second. That was what we have calculated. Are you asking this?
Hocam bu 16 MHz ayarladığımızda 16
Okay.
milyon eksi 1 yaptık.
Exactly.
8 MHz için de 8 milyon eksi 1.
There is no 8 megahertz mode. There is 80 megahertz mode for this device. Yes, if you do it 80 megahertz, exactly. If the clock was running faster, you would have to make this number larger. Exactly.
Hocam, benim aklımı kurcalayan sadece tek bir şey var. 16 MHz nasıl bir saniye oluyor? Hani normalde biz saniyeye çevirmek isterken 1 bölü 16 yapıyorduk ya.
Hertz is a scientific unit, guys. Hertz is a scientific unit, which is 1/seconds. Okay?
Okay.
So 16 megahertz means something that happens 16 times in a second. 16 megahertz means something that happens 16 million times in a second. Answer to your question? Maybe.
Tamam da şundan kaynaklı dedim. Yani biz 1 saniye için 1 yazmamız gerekmez mi normalde 1 Hz?
If that happens once in a while, yes, but this is the tick speed of the clock, the speed of this clock. This clock, this one. How many times it makes high and lows in a second? The speed of the clock. So in 1 second, it makes 16 million squares.
Tamam hocam. Sağ olun.
Okay? At each square, it is decrementing. For each square, it's decrementing. So if you make it that number, the time for this device to decrement from the maximum value to 0 takes exactly 1 second. Okay? Okay, good. Now I think you got the code. And let's do some coding. But before doing some coding, let me show you the EE315 Çankaya. Okay, so if you go to labs, lab sessions, this is the sheet. That's it, guys. This is it. It's here. So if you just download it, the password is the same. You will find this code. Guys, do you remember my Melih Gökçek Gökkuşağı project? Sorry. It was just going over the colors. It was a bit complicated code. I mean, it was one of the most complicated codes, and it was a bit difficult to understand. In that sense, it's not a good code, because a good code is the one that is understood easily. So there is no, I mean, a novelty in writing a code that nobody else will understand. But apparently I did that, and I have a code that nobody will understand. But I'll try to explain it to you. But in functionally, I'm not going to go over every line, because we don't have time for that. But if you go over this code, the thing that this code does is now, it creates, in terms of what this code does is, let me just remember what this code does. This was the sheet, I guess. Yes. Created periodic interrupts using SysTick Timer. We are creating periodic interrupts using the SysTick Timer. In the SysTick handler, we are going to change the global variables red, green, and blue. Okay? So each time, so how it's going to change, let me read it, because I don't remember. Isn't it? Those calls a function, isn't it? Okay, wonderful. Okay. Guys, I remembered now. Do you remember the previous code? The Gökkuşağı was created by using 3 global variables. If you remember that lecture. If you don't, please go to watch that video and observe the code. By changing red, green values in a specific order, we were going from colors to colors. I mean, when red is on and green is 0 and 0, it's all red. Or when red is 0, blue is 0, and green is 1, it's all green. By changing the frequency of these guys, we are creating in-between colors. To create a smooth rainbow flow, we had to design a mathematical change in these green, red, blue values. Good. Previously, we have done this. Inside, we have changed the red, green, blue values in the main code. But this time, we are going to do it in the timer, interrupt timer. The interrupt SysTick timer. SysTick timer will be called in a loop. And inside the loop, red, green, blue values will be changed. So as you can see, it makes SysTick interrupts. It initializes the SysTick for interrupts. It initializes GPIOs and LEDs. It initializes globals. If you see, the globals are initialized to certain values, 100, 800. Why these values? Because I told you to create that flow, you have to make certain values. Guys, don't think that this code is, you're responsible for this code in the exam. You know how I ask in the exam. The types of questions that I ask in the exam is something that you cannot memorize. I just ask about the logic of the design. So don't think that I want you to memorize this code or something like that. Just try to, this is a difficult code. It is possible that most of you won't be able to understand it completely, but don't worry. This is a practice. This is a live code practice. We are going over a difficult code, trying to understand some pieces of it so that we have a better experience on how to create codes. Okay? We have time. So this function initialize globals, just put globals into some values. This GPIO LEDs initialize ports 1 and 3, not the switches, to create switches. And this is the GPIO LEDs. Arkadaşlar ben GPIO switchleriyle ilgili bir interrupt açtım zannediyordum da SysTick Timer ile ilgili bir interrupt oldu. Kime niyet, kime kısmet. Bunu anlatalım. Haftaya öbürünü anlatırız. GPIO LEDs are initialized GPIO LEDs. You change the certain analog mode selection. You'll remember this direction register, alternative function register, digital enable, so that the LEDs are initialized. And finally, I call initialize SysTick interrupts, which is the code that I've shown you in the slides. Initialize SysTick, I'm trying to find it. Initialize SysTick interrupts. I put 7 to the control register, so the interrupts are enabled. Good. So guys, and I start an infinite loop. Everything will run in between. I call a function which is instant LED color. It's called infinitely. It will create the function. Let's see what happens inside. Instant LED color. Instant LED color, instant LED color. Instant LED color is, there's a nice explanation. This subroutine creates a color by using the value of the global variables, red, green, and blue, for an instant. Which means, for every value of red, green, and blue, there is a color. Okay? If red is 0, or blue is a value, green is a value, that is a color. For example, before we call this subroutine, the global variables are such that red is 100, green is 500, blue is 900. This corresponds to a color. Which color it corresponds is decided by the subroutine calculate LED timings. Because by using these colors, it creates that effect that I was talking about. Remember, so for red, we had the red. If this is 100, the red signal was going on like this. For example, like this. Böyle olmuyor tabii arkadaşlar. Onların aynı boyutta olması lazım. Daha güzel çizmeye çalışayım. For example, when it's 100, when it's 500, it is like they are equal. The green. For 900, maybe it is like this. I don't know if it is exactly like that, but these values, these global variables, designate at what frequency red will be on and off, and vice versa. So imagine what kind of a color is this? It is a very low blue value, medium green value, and powerful red value. Can you guess which color it is? Any guesses? Do you know how to guess this color?
Sarımsı bir şeyler mi?
Nasıl?
Sarımsı. Çünkü
Let's see.
kırmızı
Exactly.
fazla.
Let's see. You're right. these numbers change in between 255. So let's say it is almost done. So let's say it is 240 because it's not always on. It is not complete. Green is like a half. The maximum value for these values is 255. And this is very small. It's something like an orange. Your friend was right. Okay? So how come these numbers create those timings? It's a part of this calculate LED timings. The LED times are calculated according to this. There's a code there. You go ahead and try to understand it yourself. I'm trying to explain it, the code to you in a higher level. So instant LED color pushes the LR, pops to PC so that I can call other subroutines inside. I point R1 to red. I load the value of R0, get the value inside R1 to R0. I read the value of the red. And I calculate that timing. So I get what the next value should be. Because if it is 100, it should be 101, for example, for next time. It goes on like this. And I make the LED on according to that value. The LED on will switch according to that time. And I add a busy wait delay. Remember the busy wait delay. It takes R0, waits for an amount of time. And this code actually creates this single piece. This single piece. Sorry. This single piece. The on time and the off time. Okay? Then I continue. I do it for the green. I do it for the blue. In this code, there is no point that I change the variables red, green, and blue. The global variables. If they don't change, the colors won't change. So how come does it change? I change it inside the SysTick handler. This is not a code that is being called somewhere else. Let's look for it. SysTick handler. Where is it? It is here exported. But inside the main code or anywhere else, it is not being called because it's an interrupt. It is being called periodically whenever where is it? Whenever this guy hits 1. Or in other words, whenever this guy wraps to 0, periodically. With the period I decide in the initialization subroutine. And at that period, it increases the RGB values. How does it increase the RGB values? By calling the increase RGB function. Let's see the increase RGB function. Increase RGB, where are you? Increase RGB, as you can see. I make R1 point to red. I read the value of the red to R2. I add red R2 to R0. So they are added, increased by R0, 50. So if you change this number, actually the speed of the color change will change. Experiment on this code. This is how it does it. A complex code. Let's try to run it. I'm going to show you the code. Sorry. Because I didn't open. Bakalım becerebilecek miyiz? Okay. Okay. Yes. Yes. Olmadı. Sorry. Yes. Okay. Can you see the color? No. The color cannot be. Sorry. Okay. I'm going to restart the code. So I restart the code. Arkadaşlar color gözükmüyor. Bu nasıl bir ışıklandırma? Yavaş yavaş bir şeyler görüyorsunuz tabii değişimini. Okay. So it is changing. I'm going to change this number now. I'm going to make it 150. Yeah, or something else. 20. Yes. Okay. It's much slower now. just waiting for the colors to change slower. Guys, what I ask you is download this code, observe it, work on it, change some lines, observe what is happening, try to debug it, debug the values of red and blue in the memory, and try to understand it. It will be very difficult to understand. So you might ask, why I'm asking such a practice? I mean, you're right. Why are we doing such a practice? Nerede bu? Okay. Olmadı. Bulduk. Why are we doing such a practice? Guys, this is all about embedded engineering. In embedded engineering, this is going to be all you do, by the way. You will have some codes downloaded from the internet or written by some of your colleagues, and it will be very difficult to understand. You are going to stand in front of the code. You are going to debug it, change some part of it, debug the memory. What does this function do? How does it change? You are going to record the things, observe them, analyze them. That's how you understand the code. Unless you do this, you won't be able to, completely understand an embedded program. Okay? This is a practice I leave to you guys. Okay.